let's take a look here really quickly at 5, 6. So previously, we used a formula. In 5, 5, we figured out how do we convert an integer to in a given base, and we can come up with those. So now we're going to extend that a little bit. So we're going to say we're going to get out some data that's a little different. So we want to go the other direction, essentially, in some cases. So, and we're going to put in a couple of tests in there. So this one takes some of our basic functioning from previous. So I would go back and get it, except I don't want to log back into Cengage here real quick. But again, we have something very similar. We have, this is going to test decimal to base 10, base 8, base 2, and base 16. So let's take a look at this. It's going to be very similar. So the first thing I've stolen from my previous one is I'm going to go back and use that rep table that I created. So it's got a representation of each of these items. So 0 through 15. It's already got those pieces in there. So one of the things that would break in our previous version, though, we're gonna address pretty quickly. So I need to call that. Let's see, what do we want to call this? What did we call it? Decimal to rep. There it is. Define, and in this case we'll call it decimal to as a function. And again, we're going to take in this case, since we're calling it a decimal, we're going to say decimal, and we're going to take in the base. In other words, we're going to take in a value of 10 and convert it, what that would be in base 10. We're going to take in 10 and convert it to base 8, 10 to base 2, 10 to base 16. So this is kind of the opposite of what we just did. So there's our function we're going to create. And we know that this function is going to return something out of here. And in here, we print decimal to rep, 10, 10. Okay. So we want to return, in this case, we'll just call it rep. So it's going to pass back some content. So I'm going to make some room here, spread this out just a little bit. Okay. Get it the proper indent. So first thing I'm going to do, I know that if it's 0 in any one of these bases, it's going to be 0 in the other base. So I'm actually going to do this. I'm going to cheat and put an if statement in first. So if decimal equals 0, I'm going to return. Now, in this case, we're returning it as a string, and that way we can manipulate it and move it around in that version. So if it's 0, it should automatically kick it back and say, all right, we're 0. That way we don't have to run any math functions on it. But the other side of that, then, we can use the else. So now we need to do a little conversion and figure out how we're going to convert these back. And part of the way we do that is by repetitively dividing them. So we divide them and we get the remainder, and so we get the remainder and we get the modulus, so we get both pieces of our data. So if it were me, maybe coming up here and we'll do it on. So if I'm up here and I want to figure out what the value of 63 is in base 16, what I'm really going to do is I'm going to first divide that by my base, my 16, figure out how many places in the furthest place I have over. And so in this case, I can see that base 16, that I'm going to have a value of 3. And then I'm going to subtract those. So 63 minus 48 gives me some kind of number, probably 15. And then I can start working my way over, because what I have is a set of 16, 8, so these are placeholders, and I can start converting them over and figure out what my number is. So I'm repetitively dividing and taking the remainder and dividing it into the next biggest piece that I can. So I'm going to create a loop. And in this case, maybe we'll use a while loop. So while decimal is still greater than 0. So in other words, once we hit 0, we stop. So we need a remainder. So that's equal to our decimal. We're going to use the modulus operator there. So if I'm doing 16 and I'm in base 16, it's going to give me the remainder of that math operation, which would be 0. And so then this loop would go 1 time exactly. But I'm going to flip my decimal value based on that decimal. So I'm going to divide it, but I'm using that special, that double divide symbol, which is only going to return the integer value of it. So in this case, 63 divided by 16, I would get just the 3. Up here, I would get the remainder. And then I need to convert the rest of this. So I'm just going to use representative equals my rep table. And I'm going to come back up here and look at it. And I'm going to put it in as a remainder. Plus rep. And that returns. And then, did I already put in a return? No, I did. So now I'm going to move those back up. What do I do here? Those need to be indented. Okay. So what this does then, if I think through this, is it divides first. I get the remainder and I get the decimal portion. Now, where this doesn't work very well, in this case, if I try to put in a gigantic number, I'm going to get something a little odd. So remember that we're basing this off of our test functions here of 2-digit numbers. So we'd have to do a little more work depending on if we wanted to convert some much larger numbers. So we get our decimal, so our first piece of it, and then this gives us that rep reminder, and then we add that back in. So let's see what happens. How badly could I have typed this one? So what it should be looking at are these values here. So 10, 10, 10, 10 in 4 different bases. And what did I do here? Line 8. What did I do? Oh. Double equal sign. Alright, now we'll try it again. Syntax error expected. What did I do there on line 11? Oh. Okay, try that again. Local variable reference before its assignment. Oh, hang on. So while let's do that. All right. So here's what I came up with. So 10 is 10. 10 in base 8 is 12. Okay. 10 in binary is 1010. And 10 in hexadecimal is equal to 8. So you could go through and change some of those and try it out with different numbers. So what it would 15 be? Because one of the things we always want to do is check our work with more than one value set. So in this case, base 16, we get a value of f. Base 10, we get a value of 15. Base 8 or octal, we get 17. And then in binary, we get a value of 1111, which is, those are all the correct values. Because actually in base 16, or any of these, we know that we have 16 characters available, but our biggest number would be 15 because we count at 0 through 15. So I'm just out of curiosity going to see what happens. So I would have to check those, but it looks like it did them correctly. So 150, 96 possible. So we could go through and check those. So maybe we've created something a little more powerful than what we thought. But we can check them on the grading. So this is kind of a handy tool. We a lot of times use those, especially the area we use them here is in our networking class. Because when you type something that's like this where it says cengage.com, well, the computer doesn't have a clue what cengage.com is. What it really does is it goes out and it has to send out and say, what does this mean? I don't know what this value is. And we can test that. So cengage.com, we can use a ping command. So we said, hey, I want to ping this address. And so this value here is actually what's called its IPv4 address, or an IP address. We know a couple of things about it. So they're in what these are called quartets, and so they can be up to 3 decimals long. But they only, because it's a binary number, what it really represents is a maximum value of 1111111. And if I just hit that, I'm going to see somewhere it'll show me what that equals. So it's going to say 11111 is equal to 255 in base 10. So what that really means then is, when we go look at an IP address, it's going to be in a range, each one of these quartets, between 0 and 255. Well, it's also kind of handy then to know that FF in decimal, so in base 16, FF is actually, it's not going to show me that, is 255. So when we get those maximum values, that 0 through 256 becomes a really common thing. And in fact, inside of our programs, that's how we store one letter character. And so we've seen that a little bit already, so I just wanted to kind of refresh that idea in our brain about that. So you use them all the time, even if you don't realize that you're using them.